In this video clip, what we're going to finish is the end of the stoichiometry chapter, intro, that's chapter 8. So last time what we talked about is stoichiometry problems where we finished off doing gram to mole, mole to mole, mole to gram problems. And remember when we did these problems, this step we needed to use the molar mass of the given. For this step, we used the balanced equation. And for the last step, we used the molar mass of whatever was asked for. And so these are 3-step problems, and we did several on the last video. Today, we're going to go one step further with those, and what we're going to start talking about are limiting reactant problems. And so first, what is a limiting reactant? I'm just going to abbreviate limiting reactant with LR so it's easier, faster to write out. So a limiting reactant is the reactant that is completely consumed when a reaction is run, or you can think about it as the reactant that limits how much product can form. And so the limiting reagent or reactant is the one that's going to be completely gone at the end, and it's going to determine the maximum amount of product. So it determines the maximum amount of product that can form. So before we do this with reactions, just so you get the concept, what if we were making a sandwich? And in that sandwich, I'm just going to write a silly kind of equation. I'm going to say 2 slices of bread and 2 slices of cheese will make 1 sandwich. So if that was my balanced chemical reactions, and then I look at what things I have, and I know that I have 10 slices of bread, and I have 20 slices of cheese. So this is having bread and cheese are my reactants, and sandwich is my product. Which one of them is going to limit how many sandwiches I can make? Well, if I have 10 slices of bread, that's only going to allow me to make 5 sandwiches. And I could use my coefficients from my balanced equation to show that. I could say 10 bread times, it takes 2 bread to make 1 sandwich. And so that would get me 5 sandwiches. If I have 20 slices of cheese and I'm using 2 on each sandwich, this would allow me to make 10 sandwiches. And again, I could show that. I could say 20 slices of cheese times 2 cheese. Oops, 2 cheese. Got a little carried away. 2 cheese will make 1 sandwich. That will get me to 20 divided by 2, 10 sandwiches. So it's the amount of bread that I have that limits how many sandwiches I could have. And in this example, bread would be this would be my limiting reagent. This is the maximum amount of sandwiches I could create. And so I think when you do something like this with like a recipe, it seems more obvious. When we do this with chemicals, for some reason, the concepts get lost, but it really is exactly the same concept. And so let's just go through a couple of problems. In the beginning, we're just going to look for what is the limiting reagent, and then I'm going to throw in a couple of other terms that are used in these types of problems. So in these problems, the question is just going to be determine the limiting reagent. And we'll go through two or so of these. So in the first one, let's use the reaction nitrogen gas reacts with hydrogen gas and produces ammonia. The very first thing you need to do is make sure your equation is balanced. For every problem, always look at your equation and make sure that it's balanced. So I have 2 nitrogens. I only have 1. I'm going to put a coefficient of 2 in. I now have 6 hydrogens. Over here, I only have 2. So I need a coefficient of 3. My equation is now balanced. So the question for this one will be, what is my limiting reagent if I start with 5 grams of nitrogen and 3 grams of hydrogen? Which one is going to limit? This is like saying starting with 10 pieces of bread and 20 pieces of cheese. So we're going to have to go through a calculation to figure out which one of those is going to form the least amount of NH3, and that one will be my limiting reagent. So what if I did this completely all the way across and figured out how many grams of ammonia I'm going to get from 5 grams of nitrogen, and then I do the same thing, but I figure out how many grams I will get from 3 grams of hydrogen. This is going to be that 3-step problem done twice. So I'm going to write it all out for you. If we start with 5 grams of nitrogen, this is going to be, remember, it's gram to mole, mole to mole, mole to gram, right? These are the problems we did on the previous video. So I need the molar mass of nitrogen, 1 mole of N2. It's going to be 2 times 14, 28 grams of N2. This is the molar mass of N2. Times my next step is going to come from the balanced equation. This is going to be mole to mole calculations. And so I'm going to need 1 mole of N2 to produce 2 moles of NH3. This is my balanced equation, right? And my last step, I'm going to need to use the molar mass of NH3. 1 mole of NH3. Nitrogen is 14. Each of the hydrogens is 1. 14 plus 3, 17 grams of ammonia. And if I calculate that all the way out, I'm going to get 3.04 grams of ammonia. So now I would know if I start with 5 grams of nitrogen, I could form 3.04 grams of ammonia. What if I started with 3 grams of hydrogen? I got to do the same steps, but I'm not going to use the molar mass of nitrogen here. I'm going to use the molar mass of hydrogen. So I know that 1 mole of hydrogens, 2.02 grams of hydrogen. I'm going out to 2.02 so that I can maintain 3 sig figs. Now I'm going to use the balanced equation. And I know that it takes 3 moles of hydrogen to produce 2 moles of NH3. And my last step, I'm again going to need the molar mass of NH3. And I know that 17 grams of NH3 is 1 mole of NH3. And if I calculate this all the way out, I get 16.8 grams of NH3. Now, which of those is less? 3.04 is less than 16.8. So what's the maximum I could produce if I start with 5 grams of nitrogen? The most I could make is 3.04 grams. If I start with 3 grams of hydrogen, I could in fact make 16.8, but I wouldn't have enough nitrogen to make 16.8. So my limiting reagent is nitrogen, and 3.04 is the maximum amount of product that I could get. Now you can cheat and not actually go through all of these steps to find your limiting reagent. The reason for that is if you look at the last step in both of these calculations, these pieces are the same. And so you can just go through the first 2 steps. Different textbooks and different authors show all different kinds of ways to find limiting reagents, little shortcuts of removing things. I don't care if you use a shortcut, it's fine, as long as you understand how the shortcut works. That way you won't get confused or don't memorize it, so that then you don't remember how to do it at a later date. And it can't fail if you calculate it all the way out. You'll never have to memorize a shortcut. So, but you can choose to do that, or you could just stop the equations here, because this last step is the same. And I think if you're going to do a shortcut, that's what I would do. I would just not do those last two steps. So for example, it would look like this. If you just did for nitrogen, starting with 5 grams, and you did the first step, 1 mole of nitrogen is 28.0 grams. Whoops, I wrote the wrong thing. I did it twice. And then I said that from the balanced equation, it takes 2 moles of nitrogen to produce 2 moles of NH3. Did I write that right on the first equation? Geez, I hope I did. And so I could do this equation here and get an answer, and then I could do the same for hydrogen, but start with 3 grams of hydrogen, 1 mole of hydrogen, 2.02 grams of hydrogen, and then I could go 1 mole, 3 moles of hydrogen will produce 2 moles of ammonia, and I could compare these numbers. Whichever one would be smaller value would correlate to the limiting reagent. And so you can shorten it if you want, or you can go all the way through the problem. Either way, you'll need to find a limiting reagent. So let's try one more. Let's use a different reaction. What if we had sodium and reacted it with water, and we turn it into sodium hydroxide and hydrogen gas? If I tell you that we start with 5 grams of sodium and 8.5 grams of water, the question is, which is the limiting reagent or reactant? And so you can go through the steps completely, or you can stop halfway through or 2/3 of the way through. The key here is, though, make sure your equation is balanced. So if I look at this equation and I try to balance it, I have 1 sodium, I have 2 hydrogens, I have 2 hydrogens here, but I have a third, so hydrogen's not balanced, and I have to figure out a way to get that. So if I try to put a 2 here, so now I have 4, and I put a 2 here, I can get 2 hydrogens and 2, that's 4. I now have 2 sodiums, so I need 2, and I now have 2 oxygens, and I have 2. So that did it, balancing the equation. So again, you can go all the way through these steps, or you can stop part way. So let's go through for 5 grams sodium. Let's just be really not put in the states. 5 grams of sodium, we're going to go grams to moles. 1 mole sodium, 23 grams of sodium. Gram to mole. Next step, mole to mole. I produce, you can pick either product you want. I'm going to pick hydrogen as my product, only because it's quicker to calculate a molar mass if you go all the way through, but you could choose either sodium hydroxide here or hydrogen. I'm going to pick hydrogen. Oh, I wrote that incorrectly. Um, 1 mole of hydrogen is produced by 2 moles of sodium. I could stop there, or I could keep going. If I keep going, I would then say 1 mole of hydrogen is 2.02 grams of hydrogen. If I calculate that all the way out, I'm going to get 0.220 grams of hydrogen. If I stopped right here, I would have gotten, right, if I didn't do this part, that would have been 0.109 moles of hydrogen. If I now pick my other one, 8.50, grams of water, and I do the same thing, 1 mole of water using the molar mass of water is 18 grams. Now I need 2 moles of water to produce 1 mole of hydrogen gas. That got a little crazy. Sorry, my dogs started barking. All right, so going back, 8.5 grams of water times the molar mass of, using the molar mass of water to go grams to moles. Using the coefficients from the balanced equation, 1 mole of hydrogen is 2 moles of water. And then the last step would be that 2.02 grams of hydrogen is 1 mole of hydrogen. And if I calculate that all the way out, I would get 0.477 grams of hydrogen. If I stopped right here, the value I would get in moles is 0.236 moles of hydrogen. Now I need to compare these values, whichever one is smaller, 0.220 smaller than 0.477. This is the maximum amount of product that can form. And if that's true, then sodium is my limiting reagent. If I wanted to do this and not go all the way through, I could have compared these values in moles. It should give you the exact same if everything is right. All I'm doing is not multiplying each one by 2. And since I'm multiplying each one by 2, this one is a smaller value. And it would also correspond to the limiting reagent. So you can go all the way through 3 steps, or you can stop after 2. So let's try one more and then just see how you do. So in this, we'll start with a whole new reaction. So in this reaction, we're going to take arsenic and react it with sodium hydroxide. And we're going to make sodium arsenate, which is something we haven't seen yet. And so you need to balance this equation as well. So take a minute, make sure you can balance it. And then I'm going to tell you that you have 14.9 grams of arsenic and 22.8 grams of sodium hydroxide. And the question is, find the limiting reagent. So pause this video and try the problem and see how you do. I'm just going to go ahead and write out the answer, but you can check your work and see how you did. 14.9 grams of arsenic, gram to mole is our first step. Using the periodic table, arsenic is 74.9. Our balanced equation, again, I just went to the product of hydrogen because I did not want to calculate the molar mass of Na3ASO3. Calculating the molar mass of hydrogen, much simpler. So in this equation, takes 2 moles of arsenic to get to 3 moles of hydrogen. And then my last step would have been, if I continued this on, 1 mole of hydrogen, 2.02 grams of hydrogen. If I calculate that all the way through, 0.603 grams of hydrogen. My other reactant would be sodium hydroxide. And I could go through all of the steps with sodium hydroxide. Molar mass should come out to be 40 if you've calculated that correctly. It's going to take 6 moles sodium hydroxide to form 3 moles of hydrogen. Last step would be the same. And if I calculated that out, I'd get 0.576 grams of hydrogen. This one is smaller. This would be my maximum. amount of product. So sodium hydroxide would be my limiting reagent. Again, if you didn't go all the way through, if you stopped here and you got to the number of moles right here, you should have gotten, if you did that, 0.298 moles of hydrogen. And if you stopped here, you would have gotten 0.285 moles of hydrogen. And again, this is a smaller. And so again, it would have lent you to this being the limiting reagent. So we're going to do a few more of these, but add yet more steps to it coming up. So we're going to try, really, we'll just do one more big problem together. So here are a couple of other terms that you need to know. There is something called the theoretical yield. We've already calculated this in the previous problems. I just didn't tell you what it was. Theoretical yield is the maximum amount of product that can form. So sometimes it's worth it to go all the way through the 3 steps because you can find the theoretical yield or the maximum amount. So for example, in this problem, if we took boron trichloride and we reacted it with sulfur tetrafluoride, we get 3 different products. And again, you want to balance this equation. This might take you a minute to balance, but go ahead and try. Pause me, balance, and then click back on. If this is balanced, your coefficient should come out to be, whoops, I just put that in the wrong spot. To have it balanced, you need 4, 3, 4, 3, 3. And so here's the question. What is the theoretical yield for SCl2? So you need to be given a starting amount. So what is the theoretical yield of SCl2 if you start with 10 grams BCl3 and 10 grams SF4? So these are just like the problems we just did. You're going to go 3 steps out. You have to figure out, is boron trichloride your limiting reagent, or is sulfur tetrafluoride your limiting reagent? And again, you can pause this and go through. You're going to need to calculate molar masses. You're going to need this molar mass. And you're going to need this molar mass. So pause, try this, and then unpause and see if you got the same answer as I got. I'm going to write out the whole answer. 10 grams of boron trichloride, 1 mole, 117.3 grams, 4 moles, and the molar mass of sulfur dichloride is 103.1. Oops, and if you calculate that out, I think you're going to get 6.59 grams. And same thing, these are long, I'm just writing it out quickly. I'm assuming that you worked on this with me paused. 1 mole of SF4 is 108.1 grams. Again, you need to calculate that value. 3 moles sulfur dichloride from 3 moles of sulfur tetrafluoride. And the last step will be the same. If you calculate that out, you're going to get 9.54 grams of sulfur dichloride. So the smaller amount is my theoretical yield. That's the maximum amount of product that I can form. And then if I asked you again, which is the limiting reagent, my limiting reagent would have been the boron trichloride. So in this problem, you could go a little bit further and I could ask you a couple of other questions with it. So I'm hopeful that you're writing these out and going through it, because I'm going to go on to the next slide and we're going to refer back to some of these numbers. So what if I asked you, after the reaction, how much boron trichloride is left and how much sulfur tetrafluoride is left? How would you figure that out? Well, the first one should be easy because this is my limiting reactant. If that's my limiting reactant, then it's 100% consumed during the reaction. So if it's all used up, how much should be left over? 0 grams should be left over. 0 should be the answer, how much is left over for any limiting reagent or reactant in any reaction. But the question then is, how much sulfur tetrafluoride is left over? Still remains. What do you have to figure out? Well, we know that you started with 10 grams. What do I need to figure out? I need to calculate how much is used. If 10 grams of boron trichloride reacts. So I'm going to have to go through and do a whole nother set of calculations, but this time I'm going to start with 10 grams of boron trichloride. What I'm going to calculate is how many grams of sulfur tetrafluoride is used. So I know 1 mole boron trichloride is 117.3 grams. Now I'm going to convert from moles of boron trichloride to moles of sulfur tetrafluoride. And so going to the balanced equation, it takes 4 moles of boron trichloride to react with 3 moles of sulfur tetrafluoride. And then my last step would be using my molar mass of sulfur tetrafluoride. And if I calculate this out, I get 6.91 grams. Now, what does this number represent? This is the number of grams that reacts with the 10 grams of boron trichloride. That's not how much is left over. That's an important thing. A lot of people think this is what's left over. This is not what is left over. This is what is used. So how do I figure out what's left over? To figure out what's left over, I have to look at how much I started with. I started with 10.0 grams. This calculation tells me that I used 6.91 grams. So how much is left over? I have to do the subtraction. So if I subtract, I'm going to get 3.1 grams left over. And I'm stuck with only 2 sig figs, because remember, when you subtract, you have to look at the number of decimal places. So I can only go to the tenths. So my answer, how much barium chloride is left? 0. How much sulfur tetrafluoride is left over? 3.1 grams. There's one more calculation that you can do with these types of problems. And the type of problem you can do is called figuring out your percent yield. So this is very similar to what I had you do in the lab this week, or hope that you will do in the lab this week. And so one last type of calculation is to calculate a percent yield. Percent yield is equal to actual yield divided by the theoretical yield times 100. Now the theoretical yield, this is the value you calculate. Actual yield has to be found experimentally. This means if you really went into the lab and did this, and you were all done at the end of the experiment, how much stuff did you get? You can never really get 100% yield in a lab. Many experiments give you much less than 100% yield. Along the way, you typically don't get 100% yield. The reasons for that is sometimes that the reaction you're looking at is not the only reaction possible. Sometimes there's other side reactions that use up reactants that don't lead to your product. Sometimes you just can't get the reaction to go to completion, and so we'll say that the reaction was incomplete. Or sometimes you just lose some product along the way. This would be true if you had to transfer from one beaker to another. You're never going to get 100% out. If you have to filter something, sometimes some is stuck in the filter paper and you're not going to account for all of that at the end. So there's various reasons why you wouldn't get 100% yield. So let's use our same numbers that we just had. In this one, we said that our theoretical yield of sulfur dichloride, if you go back to that, remember we said our theoretical yield was 6.59 grams. So if we had 6.59 grams, this is the maximum we could get. If in the lab, our actual yield was only 4.83 grams, what is the theoretical, or sorry, what is the percent yield? Well, the percent yield is going to be actual divided by theoretical times 100. So I'm going to take my percent yield would be 4.83 grams. That's my actual, divided by my theoretical, 6.59 times 100. My percent yield for this one would come out to be 73.3%. So you'll get to practice that in the lab. So we could try to do one more problem on here, or maybe I'll just put one on here and then I'm going to put a quick quiz question with the answers to see how you do. So here is the problem. Here's the reaction that we'll use. NH4Cl plus AgNCO is going to turn into, I'm just trying to pick different kinds of reactions that you haven't seen. This is the compound called urea. It's a waste product found in all mammals and birds. It's actually, that's form uric acid is the white stuff in bird poop, actually. But say if we started with 8.7 grams of ammonium chloride, and we start with 15.8 grams of silver thiocyanate, which you don't know what that is, but that's okay. If we start with that, the question that I'm asking you to do is, 1, determine the theoretical yield. 2, identify the limiting reagent. And 3, calculate how much of each reactant remains after the reaction. So go through this and see if you can calculate these things out. Last thing I could say is if 2.9 grams of urea was formed in the lab, calculate the percent yield. So I'm going to ask you to do these, and it will be as a quick question after this video. Each one of these will have an answer. And then later in the week, I'll write out the answers to them all and post it, or you can email me and ask me questions on this one. But I'm not going to go through this. You can try it. You're going to have to calculate several things. Okay, I hope that helps. Talk to you all soon.